So the derivative of what's in here?
That's just 0. There.
Yes, 1.
There.
All right. Now, because we're trying to find a maximum or minimum, we take the derivative, set it equal to 0. Fortunately, this denominator, who cares? What we care about is what the rest of it is. So we've got a 1/2 times all of that. So I end up with g minus k over m, y naught minus y is equal to 0. We're solving for y. So I got g equals k over m, y naught minus y. Then we get, I'm going to multiply by m over k, so we got gm over k equals y naught minus y. So we end up with y is equal to y sub naught, again, how far the spring is stretched to be in equilibrium with a mass attached to it, minus gm over k. And looking over here, gm over k is just y naught. So the math way just to come up with the fact that it will reach its maximum speed when it passes through the new equilibrium position, the one with the mass attached to it. The beauty of it, the fact that it all fits together. Sorry, I think it's neat. Someone dared to call me cool because of it. Okay, no one has done that, but someday, someone will. Questions? All right, so this was just basically, we explored some simple harmonic motion. We established that if you're in simple harmonic motion, the motion can be described by a sine or cosine curve, usually with a phase shift in real life, without a phase shift, and nice ideal problems. Showed that the maximum speed happens when it passes through the equilibrium spot, 1 conceptually and 2 mathematically. We found the maximum speed, found the acceleration, as well as we can now find the speed at any particular point. And I know what you're thinking, going, wow, that's great, but can we apply simple harmonic motion to a different situation? Well, yes, we can. Any of you familiar with the small angle approximation? Did we do it already in here? I got a no, I'm not quite sure which way you're going, Patrick. You're not sure? You don't remember it? Maybe?
I feel like I remember something, but I have no idea.
Okay.
Like something like that. But
And Benjamin, where are you on this?
I don't think we did.
Okay. So if I asked, did a pop quiz and said, what's the small angle approximation, all of you would be wondering what the heck I'm talking about. Okay. I'm not gonna do that. All right, what I have here is an ideal string. Getting away from springs for the moment. I have a point mass right here. And what I'm gonna do is I'm gonna pull the point mass back and let go. Some people call it a pendulum. And I'm gonna take it one step further. We'll make it a simple pendulum in the fact that there's no air resistance. This string doesn't stretch. There's no friction up at the pivot point. And it's a point mass. So typically, this is the angle that is given. We are dealing with rotational motion. So I have an object that is being turned that way, or being pulled back that way, so is theta positive or negative here? That was worded, the tone of voice was off. Do you want to make, let's change the wording a little bit. Do you want to make theta positive or negative?
Negative.
Okay. Therefore, which way is the positive k axis? If we establish I hat, j hat. Or actually, are we doing that? If I'm pulling it back this way, which way is the vector theta? The direction of theta.
Would be into the board.
Okay, so this would be into the board. You wanted to make that negative, so I hat, j hat, k hat's coming out. Force diagram, what are the forces acting on the mass?
Tension.
Weight due to gravity.
Or just weight. All right. In which direction is it going to accelerate? Linear accelerate.
Tangential to the, or I guess perpendicular to the street.
Okay, so we can establish our coordinate system this way. So let's now undefine that and redefine it this way. I know acceleration is going to be in that direction. I hat, j hat. So which one do I break it up?
J hat, or weight.
Yes. Yeah, it's still coming out of the board. All right, so we're going to break weight up. Looking at the geometry of it, I've got weight acting down. I know this angle here is theta. So this angle here has to be theta. I'll just make weight larger vector there. There's my weight vector. This is theta. And I'm breaking it up into perpendicular components. So we got a component in that direction and a component in that direction. So what's this one?
Sine theta.
So I got W sine theta there, and this one?
W cosine theta.
So we're making the claim that this is an equivalent force diagram. W cosine theta, W sine theta. What are our equations of motion?
Ft is equal to W sine theta plus W cosine theta.
No.
Would it be equal to just W cosine theta?
Nope. Why not? Why is it not equal to W cosine theta?
I guess it will move down as it accelerates.
Well, we've taken that into account. A little sloppy labeling right here, but what is this acceleration here?
It's in the I hat direction.
Okay, what are the theory accelerators of a car?
The brake pedal, the steering wheel.
And,
Gas pedal.
yeah. All right, so two of those deal with changing speed, the other one deals with changing direction. This is the one dealing with changing speed. That's actually tangential acceleration. But what's the other type of acceleration because of changing direction? Yeah, so there's centripetal action going on there. So Ft minus W cosine theta equals,
Yeah.
all right, what's the other equation?
Is that J hat?
Yes, that would be the J hat equation.
W sine theta equal to MA.
17. All right, so we have these two different accelerations here. The K hat. What about a K hat? It's the torque equation. Parenthetical note that these two come from F equals MA. This one tau alpha. There's one small adjustment I am going to make here. We have W sine theta in this direction. We established early on that theta is a negative number. Sine is an odd function. What is sine of negative theta?
Negative sine theta. Negative sine theta.
So if you want a sub t to be a positive number, then you need it not minus sine theta. All right, anyway, the torque equation.
Do we know what the length of the string is?
Let's give it some clever label. How about L? From the pivot point to the center of the point mass.
Would it be L times W sine theta?
I alpha.
And then negative.
Yeah.
All right. Now we can get to where I'm going from either of these equations right here. I find this one just slightly easier, but that's just personal opinion. It depends upon which way you want to go with it. But I'm going to go ahead and take this equation right here. And so I have L mg, doing the substitution, sine theta, is equal to negative I. What is the moment of inertia of a point mass that is rotating distance L from the pivot point? What's the formula for a moment of inertia?
1/2 mr squared.
That's for a very specific case. It's a general.
Integral of R squared dm.
Okay, we can do it that way. The point mass has the same distance from it, so we can just pull R out. And so that's L squared times the integral of dm. And what's the integral of dm? So point mass is just ml squared equals negative ml squared alpha. Now we can get rid of stuff. The wrong one. So m cancels out. One of the l's cancels out. I'm left with g sine theta is equal to L alpha.
Would the negative still be there?
Yes, it would. Thank you. Now at this point, again, remember, all of this was figured out pre-computers, and so they're looking for shortcuts. Now enters the small angle approximation. What are the chances that I actually have the diagram I want in here? Yes, I do. I have it. I'm assuming all of you have good eyesight. All right, so what I have here is a graph of some angle in radians with a function of the red line, the one in the middle there is just x, or the angle. The blue line is the tangent, and the green line is the sine. That if the angle is small, so we're in this region right here, if the angle is small, they are all overlapping. Can all of you see that well enough? So the small angle approximation says that if theta is much less than 1, then the sine of theta is approximately equal to the tangent of theta, which is approximately equal to theta. So if theta is small, we now have g theta. So if theta is small, g theta is equal to negative L alpha. Recognize the relationship between alpha and theta. This is g theta is equal to negative L, second derivative of theta with respect to time. This is the exact same format as we have for kx is equal to negative ma. All right, so write a as the second derivative. It's the same format as Hooke's law, which is necessary for there to be simple harmonic motion. Well, I know that omega from this is the square root of k over m. And I know that's equal to 2 pi times the frequency, or let's put the intermediate step in, 2 pi over the period, which is 2 pi times the frequency. So if this pendulum is swinging in simple harmonic motion, then omega is equal to the square root of, well, instead of k, we have g. Instead of m, we have L. The period would be, doing the fancy math here, would be 2 pi times the square root of m over k. And the frequency would be 1 over 2 pi times the square root of k over m. Just the reciprocal of the period. So we now have a way, especially right here, not m over k, wrong one. G over L, I'm trying to get that right. Period k over L over G. And this would be G over L. Let's make sure I did not flip something wrong there. So frequency is equal, period is equal to 2 pi over omega. Omega is G over L, so it'd be 2 pi L over G. Okay, I'm good with that. Let's see how good this is. I'm going to ask you to do some timing here in just a moment. Now, in order to qualify as a point mass, it just has to be small compared to the length of the string. And I think this will satisfy that. So part of the question is, what's the fulcrum here? Got this extra string here that I don't really want. Don't need that. So this is a slick surface here, the string is slick, and so the pivot point is going to be basically, so it rotates, pivot point is actually top of this. So I need to measure that distance, get L. So from the top to the center of mass here, 105 centimeters. L is 1.05 meters. Let's use this to solve for the acceleration due to gravity. All right. Now, when I pull it back, I can't pull it back too far because then I lose my small angle approximation. All right. Ready? 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7,